create an RMS intro for people that know nothing about RMS, and I see many people here that know quite a bit about RMS. Who knows nothing about RMS? Good, good. So you guys keep me honest, pretty please. Because I have this tendency to write something and then, oh, it's connected to this other thing. I need to explain that thing. And before you know it, you get this mess. But you can read it at your own leisure, I hope. Okay? So let's get going. So it is an intro, but there's a lot of stuff there, and we're going to skip quite a bit. Slow me down if it doesn't make sense, and tell me to. It's just too much stuff. Let me go. I want to go a little bit about the definition of RMS and the history quickly. The various file organization, that's really the critical part for you guys, the file organizations, and the APIs. How do I talk to RMS? Where does it sit? How do I control it? Okay. I'm not going to do global buffers, and I'm not going to do bucket size details. I'm not going to talk about when compression helps and when it doesn't help, because that's not relevant yet if you don't know how to use the beast. If I do go there, raise your hand and tell me not to go too deep. All right. So RMS, record management services. RMS provides access to chunks of data called records, but you may call them rows if you come from SQL land, right? Or entries or print lines. Those are also RMS record, COBOL programs, right? They're objects, they're blobs. For RMS, they have no structure for RMS itself. The application defines the structure. So we are record driven, so we are not byte streams. So we cannot, it's just an opaque blobs of bytes and you get the whole blob. You don't get the first 5 bytes, you get the whole blob. The unit of work is the entire records. There is a structure often defined by program include file, maybe a dictionary, either local or client-based or server-based. It really doesn't know about the structure other than key segments. RMS can, in the index file variant, look up records by key value. Of course, it needs to know where those keys are. So that might impose, so often those keys have even a name. So it could be social security number, a silly name, an address or something like that. So now you know at least these bytes are an address, but no more. And this is one of those too deeps already, but RMS has a no, but the word comes up in my presentation. I want to use it, the word stream. And RMS has a notion of record stream. So you're going to open a file and you're going to read records, but you can then also, and now you're reading record 1, 2, 3, but you may also want to skip to ABC in the same file and read A, B, C, D, E, and then go on 4, 5, 6. You can have multiple positions in the file, and those are called streams. So but normally one open, one stream, get a record, be done. Records live in some, just defining some terms, if you like. Those records that we talk about live in buckets or buffers. We're not going to explain exactly how big those buckets are and so on, but the records live in chunks of blocks on disk and are moved into buffers where they're accessed by RMS. And those buckets live in a file. This thing moved, that's okay. RMS is a long history. It started in the 70s on PDP-11s with Ristas and RSX11M, terms you don't know. The critical thing is that in those days, we were 16-bit PDP-11s. And that 16-bitness still shows through in the on-disk structure. So most of those files are compatible from 1970, 55 years ago? Forever, right? Come along VEX VMS, we now are talking 32 bits, and the in-memory structures, everything changed to 32-bit addresses, but the files on the disk are still the same. And then sometimes in I think it was 7.3 in the 2000s, 25 years ago already. We finally, the 64-bit became widely available for us to work with. And RMS adopted a limited 64-bitness in the sense that it had the opportunity to make massive buffers and massive buckets. It didn't go there. What it did focus on is to give your program access to data in what we call P2 space, in the extended data space, and you can have lots of records in your area. So we need RMS to say, read a record for me and put it in 64-bit space. Right? So that level of 64-bitness is there, but the files on the disk are still the files on the disk. I call that limited, but the records are still limited 16-bit length, 32K length. Okay. So yes, we went 64-bit, but there's the files themselves are the same. But except for read-IO. So RMS, this is one of those tangents. RMS in general, the record management system, but it has a sideline where you can say, give me this many blocks and write me that many blocks. So now we're approaching streamness, except in block level. And for those with the 64-bit interface, you can go to gigabytes of data in one IO. Not that you would want to, but RMS from the get-go is meant to be very protective because it wants to offer you a shared environment where you update your records. They live in a file alongside of somebody else's records. You don't want to trash them. If you're updating a record, nobody else should be updating them on that computer or in the cluster. Because we're going to, and we'll go back over that, because we're going to, in order to get to a record, we read a bunch of blocks from the disk, we find our record and we update it. But now that bunch of blocks in the disk is in my process, and next to it is somebody else's record. So we don't want my code accidentally writing over your or somebody else's record. So RMS did this by locking, first of all, right? So when we try to go for a record, we want to serialize that nobody else gets there. And I'll stop there. We find the block on the disk where it's in, the bucket. We lock the bucket. We find the record in the bucket. We lock the record. We release the bucket. The record is yours. Now you can play with it. When you're done, update, we will release the record lock. Okay. So we have a level of controls. And we have a file lock. Under there is the VBN lock, and under there is the RFA lock in levels. The colors don't shine too well, but that's okay. Those locks are visible with Analyze the System if you wanted to go there. Oops, that's too deep again. You didn't. But if you're stuck literally on a lock, that's where you go and play to see who's holding up what. Then the locking is the one start to protect itself. The second part is we run in executive mode. So we run on an inner mode, not kernel mode, but executive mode between user and. So we had our locking, we run executive mode. If this is a picture just from the guide to files, maybe snarfed it there. You have a big process memory. In the process memory, you have your code and your user buffer, and now you tell RMS, go fetch me some records. RMS has space in systems in executive mode protected where your program cannot override it. So the gain is the user program cannot muck with RMS buffers. That's the gain and the goal. Those buffers will be because those buffers will be shared eventually, but through the storage. So if one process has this buffer and another needs the same bucket and the other needs the same bucket, he can write it out to the disk and pick it up on the other side. So they will be shared, but not in a single buffer, except for global buffers.
Too deep.
So it's sort of okay to destroy your data and write all zeros over, but you're not supposed to write over somebody else's data, and we solve that. The pain is the pain that you will not notice as an introduction programmer, but whenever we say you got to do something, we're going to do is change mode to executive instruction to get at a different operating system level. And once we're in there, we don't trust nothing no more. We're going to use our internal privileges to touch data that's being pointed to by a customer, by an application. So we need what we call to probe the addresses that the customer provide, the buffer addresses that we could write anywhere. So let's take the simplistic example. We don't want you to say, read me a record, and oh, by the way, put it over my privilege mask. And now I have all the privilege in the world, right? We could do that if we didn't probe stuff. So we have to do the change mode exec. We have to probe all the RABs and the FABs. Those are the handles that we use to get to the data. And obviously the record buffers and the key buffers. This change mode exec and this probing is relatively more expensive on x86, but they're so powerful anyway. So who cares? No, you don't notice. It works fine, but there is an extra price to pay beyond the VAX having those as native instructions, going to Titanium, going to the x86, and emulating layers, emulating systems. And gain pain, extreme pain, if RMS doesn't do it right, you're in executive mode, the process will die. And if you choose to, the system will die along with it. Yeah. That hasn't happened much in decades, but we did release an incomplete patch earlier this year, which will do, which makes that.
5 bug check fatals.
Yeah, you should have called me earlier.
But I think the important point to make here from a security point of view is where other operating systems will allow you to be subject to ransomware, the system will just bug check and say, I'm not doing that.
We're not going to go there.
Yeah.
We're doing okay so far? Nothing scary. So all that is working, but there are some user tools that are interesting because the data sits there on the disk. So if you are allowed to read the data, your data and your neighbor's data, you have access to the file, we could do something with it. So the best one is really the CRTL. So if you're using the C programming language and its code to read records, then C says, oh, this is a normal file, a normal RMS file without any complications like an index file. I can just fetch the block and figure out where the record is and where the next record is and where the next record is. So they don't read in a non-shared environment. So they can bypass all that probing and all the change mode to exec and read quite a bit quicker. CRTL does that, COBRTL does that, and SORT does that as the native tools that are, when appropriate, read directly bypassing RMS itself. Some tools even understand index files, the most complex version of the file. We're going to talk about index file. And really, I want to emphasize this particular one. Look for it at some point. Select used to be a commercial tool, and it can read index files so much faster than RMS can. It's been a lifesaver for some business couldn't do their work if they didn't pre-select 1982 data. No, I'm dating myself. 2023 data and sort it by social security number and give it as a chunk to the next processing step. If they had to do that through the RMS interface, it would take 5 times longer. Really nice little tool that has its own data definition language.
So who was the third party that developed that?
It was EGH Software here in Waltham, Mass, not too far away. They made it fully available. The code is there, macro code. The guy is still willing to take calls. Nice tool set. It's been running for 30 years.
Does it work when the file is
open
by somebody else?
It does, and it's almost the same risk you take with backup/ignore equals interlock,
Okay.
where you just take a snapshot, but it's actually less of a risk because it is following bucket pointers. So backup knows nothing about the file,
Right.
but at least an RMS is of the careful write nature, where if it puts it's going to put a new set of data, a bucket of data in the file, and needs a pointer to that. It will not first write the pointer and then the data, because then if somebody were to follow the pointer, there's nothing there yet. So it will carefully put the data there first, right? And then point to it. So as long as you're following the pointers, the odds of finding a bucket in transition are non-existent. It's there or it's not there. Now, I cannot guarantee there's no locking between records, right? There's no consistency, but you get all your data. Nice. And I got a little tool, and hopefully that works this time on this presentation directory. There should be a zip file with a bunch of tools in both FACS, Alpha, Titanium, and x86 executables if you don't have the compilers and the sources. That should be there too. So how do you learn about RMS? That's being here, it's just an intro to whet the appetite, give you some keywords, give you some chance to ask. RMS reference manual is the gold standard, but it's not an instruction manual. It has just, this bit does that. This pointer expects this, but not why. A little bit in the text, it says, this will have some overhead, this will allow you to do this. Let's say there's a bit, say, TMO, wait for the lock to come available. That's pretty obvious how that works. But you kind of need to know what to look for, right, in those spaces. OpenVMS recommended utility reference manual has more than people have been skipping that manual, but that's where convert is described and where FDL is described in detail. Guide to file applications, it doesn't say the guide to RMS application. The guide to file application has a pretty good overview of RMS, possibly better than this presentation. So go there. But it is spinning Rust oriented. It describes how disks are stacked and have cylinders and blocks and tracks. Ignore that stuff. Data is very, very valid. The Programming Concepts manual has a very good section on the 64-bitness if you needed that, because it's not, the RMS manual is not easy enough to read for that. And I think, I forget which one is 1 or 2. One of them has a couple of user open examples where you can say, I want my Fortran program to open an RMS file, but I want to tweak the way Fortran would have opened the file to give me a little bit more locking or less locking or something like that. And so that's called a user open, where you alter and where you replace the normal open with your code to do the open. All right, finally. RMS deals with records and files, and it has 3 major file types for that. So now we're starting to come closer to the records themselves and the disk. The files can be either sequential, relative, or indexed, and we're going to take a couple of minutes on each to see what they do. So sequential file is your boring file. This is your text file, your program source, but also your object file. It might not be, it doesn't have to be readable. It's a bunch of records, record after record. And you deal with it by doing read next and read next and read next and read next until you're done. And maybe you want to rewind and do it again. Fine. It is as you go through the file and the records pass by, there's no seek and tell in like the Unix offer, but there is a handle comes by, and you can remember that handle. It's called an RFA. You can say, I saw that record, that's an important record, I'm going to remember its RFA, and I can jump right back to that particular record if I wanted to pick up from that space again. So we have a limited backwards, but only if you've seen the place before. You can go back to where you've been, but you cannot go back to some random space. And you cannot say, oh no, I want to read the record that I just read, unless you had remembered what it was. If those records are fixed length in size, you can calculate where it should be, right? That seems pretty straightforward. So RMS does allow that. So we have a direct random access for fixed length records. So we still have a sequential list of records, one after the other, one after the other. But since they all have a fixed size, if you say I want record number 12, 12 times 40 bytes equals 480, no, I don't know, byte offset in the buffer. Let's go there and fetch the record. Follow that? And you request those kind of things by in the interface by setting fields to values. You say, I want to operate in key mode and no longer in sequential mode. We'll come back to that. But there's no seek and tell. Those RFAs, once you get the hang of it, you can make them up. But nah. So that's a sequential. That is the basic file on VMS, right? With me? Relative files, they kind of look like sequential files because there's still a bunch of records following each other, but they're not records. Now they are cells. A cell contains a record and a flag saying whether there actually a cell can contain a record, and there's a flag saying that there is a record, there is no record. And this allows for sparse files. So you can have a room for 1 million records, but you only write 5 of them in the file. Now, if you then say, read all the records, you won't get 1 million. You'll get those 5 that you wrote, and will internally skip all the non-existing records. So the relative file buckets full of cells. The cells, forget the span buffer. If you're starting to fill chunks of disks with records, you have to decide when you end your chunk. Do you want to say, I'll skip to the next chunk because it don't fit? Or do you want to say, I'll write 60 bytes here and 40 bytes there? We call that spanning the buffers. So the cells do not span the buckets, they will live. So therefore, if we read a chunk of data, we will have entire cells. We don't have to worry about gluing stuff together. Records have a control byte, direct access to a relative record number, just a 32-bit quantity. So I want record number 1200. Read next is available, even though it's, so we will have to skip internally. And random to RFA is also available. You can remember the ones you read, but just a record has a number, use it. You should end that RFA. And there was one. And then we come to the big boy. This is where the business data is stored, the index file, right? So the index file, again, like the relative file, a bucket full of records, and the records do not are entirely contained within a bucket. The records again have a control byte to say, am I actually there, or was I there, but I'm in a journaling environment and I'm not quite visible yet because the data wasn't committed yet, those kind of things. Or maybe I may look like a record, but the actual data is over there. There's all kind of internal structures that are controlled by flag bytes. We have direct access to the file based on key values. We'll talk more about what kind of keys. We can have multiple indexes. You can say, so if a file, and we'll do the stupid thing, a social security, a name, and a phone number, because you have to decide what are you looking for. I'm looking for a social security number with value 1, 2, 3. So I'm going to follow the index that holds the fields for the social security number. Same as SQL databases, right? So we can have multiple indexes available, up to 255 probably, because that's they're counted in a byte. I think once you hit the 10, you should be wondering whether you should be in an RMS index file at all anymore, or you should be in a database or something like that. 1 is the 1 is dominant, 3 or 4 is pretty normal, 10 gets in the abnormal space. Do we agree with the non-intro users?
And 6 gets over that admin space,
Yeah.
right? We got that one with the 6.
Yeah. While the files are organized as chunks of data following each other by primary key, you can read backwards, which is recently implemented, recently being 7.3, 2000, something or other, and where, because IBM required this for its COBOL, it had a prior statement apparently. So when we are normally, so an index points to various places in the file, you're reading along, now you come to a point and say, I want to read prior. Oh, let's go back up the index, go over the index, down again, and find where I should go. So it's over and down. Random reads are through RFA are also available, but in index file cases, those random reads by RFA are very critical because they direct you directly to the data. You skip all the index stuff and the pointers and the key values. So there you can avoid, if you know you're going to come back, that's where you can save a lot of work. And then a little side note there, one of the magical tools that has totally disappeared from the Earth, data tree.
Yeah.
Remember that? And you could make collections. So those collections were actually arrays of RFAs. So it remembered every record it selected. When you select and then you do something with it, and it would remember just the RFAs, not the key value or anything, and it could jump back straight away. Because we have all this structure in index file, don't remember this now, we have an overhead in the bucket to describe what the bucket is and where we're going next, and we have an overhead in the records. So in that sense, they are not the cheapest because it's extra stuff, and yet they are the only file file organization that natively offers compression. So actually, index files can take less space than your data is, and often does. All right. So now we talked the sequential files, the relative files, and the index files, and the records within there. Those records have a shape, if you like. They have a format, and the dominant VMS format, if you just say create a file, hello world, stop, is going to be a variable length record data. If you do the hardcore programming and you just say create API, initialize your structures, create a file, that's what you're going to get. Okay. In a variable length record, the data is preceded by a 16-bit record length word, PDP-11s again. And actually the upper bit is reserved to say that I have the space, but I don't really want to be here, skip to the end of the block. So we only have 15 bits to record, so we have 32 KB records is the max, period. So if you want to store a picture in there, it ain't gonna work. But if you want to store a database entity in there, it's probably gonna be fine. It's a lot of data for one object, but not for a picture or a voice recording, anything like that. It's also eminently suitable for binary data. So just because I say this is the basic RMS file, your login.com or your program code, it doesn't have to be readable. It's just lots of data. And then there's no span block. In the next organization, I need to mention, but as an intro, people, please skip it. Because I can't stop myself, is variable length fixed control, where you do have that variable length, but there's also an extra part of the record where you can put, let's say, I think one of the examples, Fortran programs had line numbers in there. And so if you stuck the line numbers in that fixed control, you could not see them while you're doing your editing, but they were still there. And some editors have used the VFC also to have their line numbers hidden from regular view. If you know, you know, but otherwise just don't go to those files.
So, I cover this in my talk, which I'm doing, but there is an issue. If you, in DCL, if you just open a file to write, it naturally goes into that VSC format, and that can cause issues if you then want to merge those files with other files generated by other applications. So there is a trick to do it in that you
I stopped myself on not putting that there.
In var, and then open it to append, and you can retain
Exactly.
version.
By default, it does that.
Yeah, just little tips for you.
So, main format, variable length.
Yeah.
VFC, a variation on variable length. The easiest format is, of course, fixed. Allows direct, because it's just a predefined number of records, bytes in a record. It allows direct access by record number. I mentioned that earlier. And on this, the record data is still 16-bit word aligned. So if you have an odd number of rows, we'll start it at an even boundary, because that was more efficient on PDP-11s. That's fixed. How simple is that? UDF says, we're getting close to the byte stream. Now you can finally say, read 12 bytes and deal with it. And maybe in 12 bytes, you see that the next chunk is 500 bytes, and you can say, read 500 bytes. Right. Very close to that. We're not using that in VMS in general, UDF, that I know. Place, maybe it's underutilized because it's very close to the stream that you wanted to use anyway, but there is there's no locking notion to it or anything like that. Well, you can lock a byte. You lock your first byte you ask for, that's the lock. But if your neighbor locks the next byte over, you're still overlapping. So that don't work. It's very minimal support by command line tools. Some of them handle them, some of them don't. And now we come to the modern dominant file. So the variable length file is all we had, but then these stream files snuck in. This Unix people.
It's always the Unix.
It's always the Unix people. Now, in stream, you'll feel right at home coming from a non-VMS environment. In stream, the records are terminated by special characters. So we have a blob of data and an indicator, this is the end, and a blob of data and an indicator, this is the end. We have flavors of stream, and the normal one is stream LF. I would like to think. Does anybody use stream CR? But the normal, so a line feed terminates the line, which is the thing that Unix does. Line feed \n, hexa, decimal 10. If we see one of those, okay, next record coming up. Stream CR, similar, but we use carriage return for the separator. And then there's the one that sounds like the one you want, stream. That is bizarre. Because the terminate is line feed or carriage return or virtual tab or form feed. So now where with your stream LF, you had to be conscious to not have a line feed in there and accidentally terminate your records in binary-ish data. The stream becomes unmanageable in that sense. It's similar to the Windows default because it will also terminate on carriage return plus line feed. So those will transparently work. There's some bizarre ristas, I think, semantic skip leading binary zeros in records. So the record that starts with all zeros, those zeros don't get returned.
Yeah, when you say, I'm sorry.
No, you.
When you say the terminators or line feed carriage and so on and so forth, is that concurrently or can you choose?
Any one of them. No.
You can't choose.
You can choose. If we see a carriage return, it terminates. If we see a form feed, it will terminate.
It's impossible.
Well, no, it makes sense in the COBOL-ish report lines, right? The next page would have you print at the bottom of the page, and you have a form feed, and now you go. That's the next record. That would make sense. But you could also have a form feed, new line, But then you have an extra new line. So in that sense, there it makes sense. Did you have a useful usage of the stream?
No, it's not useful for the last one anyway. So was that encounter? I don't recall seeing.
No, I just assumed that we picked it up from for risks compatibility.
I never encountered.
Yeah. Again, if you know what's happening here, fine. Otherwise, just stay away. Use StreamLF, which is what you're going to get if you use a CRTL. You write a Perl program, you write an awk program, you're going to get a StreamLF file. Let's do a quick demo. Now you have to pay really close attention because we're now the nitty-gritties, but I think we can handle it. If I create a variable length file, I don't say anything, so therefore it becomes a variable length record file. And I stick in ABC, ABCD, ABCDE, 3, 4, 5 bytes long. Now I can I can dump the records and I get that data back in binary form, but I can also dump the block that holds the records with me. And what do we see? So the way VMS dump works is we have, because of the little endian, big endian thing, we have the binary data going here, 0, 1, byte 0, 1, 2, 3, 4, 5, 16. And we have the ASCII data going the other way, byte 0, 1, 2, 3, 4, 5, 6, 7. So what we see here is before ABC, we see 2 unprintables, because those unprintables actually are a 16-bit word telling us how much data to expect. Here's that 16-bit word, but watch that. There's a 0 to align it back on a 16-bit boundary. RMS will not return that 0 to you because it knows it's a 3-byte record. Then we get the next chunk, 4 byte, straight 4 bytes, 1, 2, 3, 4. And we get the next record, 5 bytes, 1, 2, 3, 4, and a terminator. And it's the last one, skip to the end of the block. That's that minus sign. Tricky? Not really. It's why not? Why not? It's a good way to do things. You could make a table of record lengths, and some storage system do that. First record in the bucket is 3 bytes, second one is 4, second one is 5, and then find your way based on that table. It's another way to do it, but we have the length in the record. Now, if I take that same data and I convert, and oh, this is such a sweet trick because I implemented the code in 1991. The trick being where we always had /FDL is the file definition language. You always had to point to a file containing the file definition language, but I changed it to be an inline piece of string to do it. I don't need to create the tiny files. So convert. The FDL definition is I'm going to have a record, and the format of that record is StreamLF. Fairly straightforward. But I could also say, and the block size is 200. That's not legal, but it's fine. I could say many other things in that file definition language. But I convert my variable length file to a StreamLF file. Okay. Now I'm going to dump that StreamLF file. And isn't that simple? The data reads ABC and unprintable being a line feed. ABCDE, unprintable being a line feed. Very simple structure. Okay. Now you know everything about sequential files. Right? What else is there to say? Pretty much it. Those were sequential files. I think my intro to the relative files that I mentioned, where I have the cells and the flags, that's probably enough for now. You can read them up in detail, read them up on that slide. Records can be within the cell. There could be one of those variable length record counters, so that record length word could be inside of the cell. It's relatively funny, huh? Wasteful, because you have these buckets and this overhead and the cells, and if you write record 1 and record 10, there's this gap that's wasted space. If you had an index file with proper keys, 1 and 10 would be next to one another. Bucket size is too often default. People just don't think about it. They make the tiny, just enough to hold a record, where maybe it's better to hold 10 records when we're dealing with. and direct access. And one little surprising fact, I still think it's surprising, if you convert a relative file from the old version to the next version, we pack the records. How do you know what's where anymore if you had those spaces? That's how it works. And that's because when you convert is a RMS tool that just says get. And I earlier told you, when you do a get through a relative file, we will only get the actual records, not the gaps. Crown jewels, index files, index sequential ISAM files, they're called also, right? Index sequential access method. We have buckets full of records. We have the maximum bucket size limited by good old PDP 11 defined structures, 63 blocks, which are then 63 blocks, which would allow for a 32 KB maximum record size. Okay. Sorry, that's all you're going to get. We did not change that with 64-bitness or with integrity or actually you said on this structure state. If you just say create an index file, we will create a bucket that holds 2 records. That seems fair. But this is again from fax days and 1 megabyte and 5 megabyte RK05 drives where space was limited, address space was limited, disk space was limited. So if in order to make it work, I need to be able to fit 2 records, then all I'm going to create space for is 2 records. Because that allows it to work. But it might not be optimal at all, and it might not be what you want to do today at all. You're still stuck to those defaults. Direct access through key values, yes. Multiple index available, yeah, read next. Read backwards, that's a little bit duplicate, sorry. The records, that was the bucket in the index file that holds the records. And then index file records, they do not span those buckets. They fit entirely in a bucket. They have a control byte again, whether C is present or not. We can be variable length. And in the variable length case, we can just stick one record to the next, to the next, to the next, to the next, unlike the relative files where they all had a fixed size. They can be compressed, making the record storage effectively variable length. So even if my records were always 1,000 bytes, don't make them 1,024. It makes no sense. I see that so much. The records being 1,024 bytes because it's a nice even number. Well, we slap 11 bytes right on the front. There goes your 1,024. But silliness. The compression is very simplistic. We don't have a LVIS or whatever they're called. We don't have a table of nice patterns. The data, we have a simple repeated character count method, which is wonderful for those COBOL programs printing print lines, 132 bytes and 80 spaces at the end. We just say 80 spaces. That's 5 bytes if you look at the details. But in order to do that. So that works well. Chunks of zeros, chunks of spaces, underscores to separate a line or something like that. They collapse into 5 bytes. Simple. Which also means it doesn't take much time at all to uncompress them or recompress them. Key values can be compressed with a simple repeated partial string method. So Hein and Heuvel, I can say, okay, I can take the first 2 bytes from Hein and use them for the next key, which is Heuvel, but I don't need to store those 2 bytes. At the 2 byte level, that's not efficient. But if I have customer 1,000,016 and customer 1,000,017, now I can save the 7 bytes, right? 6, who's counting? The header. Okay. And then because we know that a key should be 20 bytes and we only give you 16 bytes, then we assume that the last byte needs to be repeated to fill it out. So we compress that away too. And 50% is the compression happens in the indexes and at the data level. At the indexes, that compression can easily do 70%. At the data level, it's more in the 30% area that we say for that. It's in good space and processing savers. That's what people don't believe. They switch, they don't enable, and you don't need to go there because you're beginners, and as long as it works. But eventually you want it to work well, and you start to think, well, compression is going to take a lot of CPU cycles to uncompress. No. Yes, it takes CPU cycles to uncompress. But because you can now fit 5 records in a bucket instead of 2, when you say, get me a bunch of records, for all the I/O effort and all the locking effort, you get much more bang for your buck. So you actually save CPU time by enabling compression in general. Records can, you write an index file, you write a record in there, fine, it sits in a bucket. But it's not, might not stay there forevermore in that spot. We will remember where it is for you, don't worry. But the index sequential access method, the sequential part of their index sequential access method is that records, if you say, give me the next record, give me the next record, they will appear in order of key. And so if I had inserted, if I started out writing an A and then writing a C, but now I write a B, it needs to show up in between, and the C record has to move. Hopefully there's room. There might not be room. It has to, perhaps I have to find new free space in the file to put that C record there, or maybe leave the A and put B and C in the next bucket. However, we deem that the best way. So records can and will be moved to physically store them in primary key order. So the physical storage is primary key. That is, what's the term? RDB has a couple of terms for that too, I think. No, they don't matter. So they have to be stored by primary key order, and we will make it so. But your program might have remembered that RFA, might have remembered where it lived. So now we go to this process that the RFA has the original place where it lived, and if we move a record, we leave a little trail behind. Here is what you expected to find, but oops, the data moves to its natural sequential position. But I can follow the link and hop over. So we leave behind the record retrieval vector, and that's it, but that is overhead. Much more complex structure. I'm going to have a picture soon. Maybe the next slide. I just not yet. We'll have a picture soon. When we're talking more details on the index file, is one of the important part is what do those keys look like? Is it always a piece of string? No. It's often a piece of string, and so just a basic data type, unsigned byte, no collating. That's the default. So the uppercase A sorts before the lowercase a. They're not sorted together. The lowercase a sorts after the uppercase B. Nothing, no language at all. Just 8 bytes. We have several integers, 2, 4, and 8 bytes, where that 8 byte is very, very heavily used because 8 byte nicely matches the VMS internal date and time storage. We can do packed decimal because RMS index files are almost made for COBOL, right? That's what we had to support to begin with. COBOL uses packed decimal strings, and it does have collated strings, and people have used them. I've not run much into it. Anybody ever used collated strings where we can have a full natural definition on how to sort them? Very little used. So those are the 4 big ones. Then each data type can have an ascending and a descending variant. So you can sort Z down to A or A down to Z, what gets you the next record. String keys and only string keys can have multiple segments. So you can say, I have a record from 2025, 1022, but you have many of them. Then somewhere else in the file, you have, this is order number 5 for that day. And now you can have, I have 8 bytes for my date and I have 5 bytes for my order number. And together we form, they don't need to be adjacent. Now, this is VMS. Integers are a little endian, so they don't sort as strings. You've been very careful about it. That if you put a date as a binary number, you cannot make it a string key because the bytes are the wrong way around. You can play with that with those segments, but we don't. Picture stolen from the other. Oh, this is like a wake-up call. The white screen. That's the other presentation I have. You can find it in the Malmo sessions. That's the much more detailed index file and the specifics on tuning them once you know why you even use them. It's good to know that they're there and where you can use them. I just want to show how it sort of sticks together. So an index file, as you might surmise, needs to know what it looks like on the inside. So that's inside the file. And so we have a prologue. To have an introduction, we describe where the zones in the file are. We describe how the key looks like, where the index starts is the key, how many bytes the key is, which offset in the record the key has. That's all defined in the key block, and which then points to a B-tree index. Do I need to go there? There's a set of data where you say I have a key value and a pointer to the next bucket, another key value and a pointer to another bucket. Those key values point to the highest key in use within the bucket. So if I need to find record 4, I go down. 4 is less than 6, so I should go down this path. 4 is less than 6, I should go into this path. 4 should be, if it's there, in this bucket, but it ain't. Right? If I needed to look for record number 9, number is the wrong word, with key value of 9, then it's larger than 6, so I need to follow the next pointer, and there was really no next pointer. That was the highest key in the file. The highest key in the file, 9 is less than the highest key in the file, 9 is less than the highest key in the file. If there is a 9, it would be in that bucket, but there is no 9. With me? And then you now see that data in primary key order. Somewhere in there, it also says the first data bucket is over here. So if you say, open this index file, get record, get record, get record, we follow the primary key definition, find out where the first data bucket is, and start reading, 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 reading. So these have pointers between them. This is still a build slide, good, it still works. 1 key, 2 keys, 3 keys, 4 keys. So the alternate key could be last names. And the same story happens. If I need to look for Hein, Hein is less than Smith, Hein is less than Jones, Hein should be in this bucket. Now, and then what? Where does that now I know where it should be, but if I find it, how do I find the record that goes with it? We use those RFAs. So we point back to the real data record from the ultimate key index to the main data record. And how do we do that? Because when we stored those records, we got these RFA values. This was bucket number 4, record number 1, bucket number 4, record number 2. They don't need to be in order because we keep them in order. Bucket number 8, record number 6 was inserted first. 3 was inserted later, so it's the second record in the bucket by RFA terms, but it's the first record in key order. You see how that works? And on the alternate key, what we remember is the 8,1 to point to this record. So Jones apparently had primary key value 6. This is the core of it. If you get this picture, so you understand the index files. Close enough? Any more detail? And time is sort of up, isn't it? And I didn't get there at all. APIs. How much are we into lunchtime?
It's not a problem. I mean,
It's
it
not.
starts in 3 minutes.
I'll go quick. Try to go quick. Famous last word. That ain't happening. So RMS, when you write an RMS program, then the official RMS interface is a set of control structures. We don't do a list of arguments. They appear like handles. We have FABs, file access block, RABs, those stream access blocks, and those are identified by a little internal handle pointer. Okay. The fab will point onwards to the file name and file processing option. The RABs will point onwards to the key buffers and the record buffers and the timeout counter and all those details. So, how do I do this? So we don't remember the address of the fab or the RAB. We remember an identifier that's stored within there. An ugly anecdote, not proud of it. 79 or so PDP-11s, no storage space, no memory space. Customer needs to open 200 files. We didn't have the room for 200 fabs. But the only thing that matters is the IFI. So I create a template fab, and I clear out the IFI, open a file, remember what the IFI was, and go to the next file. And when I need to close the file, I'll put the IFI back quickly. Now I can close the file. Great. Until a user subroutine set the bit in the fab saying delete on close for one of the files. Oops. You see where this is going? From that moment on, every file was deleted on close. That was not pretty. But silliness. But it's still a useful tool. If you have a bunch of files to deal with, you could have your own structure with a file name and this identifier and say, okay, I'll just recreate my fab when I need one. We have lots of routines. We're using the file. This is straight from the manual, sort of in alphabetical order and with the text from the manual. But the important ones on the fab routines, the file level routines, are close and open, right? And create potentially. You can have file name handling with fabs. Say, find me the first file that starts with ABC, that kind of stuff. Then once you've opened the file, you're going to connect a stream to it or multiple streams. And the stream allows you to read records. So for that, the connect associates the RAB with the fab, stream with the file. And then once you have that, you can delete, you can find, which is COBOL start clause, find locates the record but doesn't get you the data just yet. You can get the record, yes, that's critical. You can put a new record. You can rewind to get back to the beginning of the file. And you can update. It's things you expect, right? It's a bunch of extras. And then we also have this block level access we call read and write. What does a fab or a RAB look like? And forget this as soon as I skip to the next slide, but it's just a C structure with an integer with bits set for options, with a short set user record size, my buffer, the actual record size, the RMS buffer, the pointer to the user buffer, where you're going to write it into, a pointer where it was written to. Those, you kind of expect them, but they are annoying to deal with. These RFAs in there too. They are mostly aligned, so you see a quick fill here, such that we can do a move quad on the RFA instead of a move 8 bytes. Big deal. But you don't, unless you write macro or C programs, you don't see those FABs and RABs because the system takes care of that. So take our highest level language, TCL, right? Isn't that wonderful?
Yes.
No FABs or RABs. It does do what I mean, kind of semantics. Open a file called UAF based on a copy of this UAF. I learned not to do it on the live. Another anecdote. Read key is a value. What else do you expect? From this file, which would be the fab, into my record, which would be the RAB if you were programming it, right? And then I get the data in record, and I can use the DCL write extract my username. Actually, it's 32 bytes, but 12 is enough for all I know. And then I write the owner name, which is started with a byte count. It's a 32-byte string, but the first byte is how many bytes are valuable. So you need to find the first byte and use it as the length for that section of the record. And then it writes my record, my name. Now, if I say without a key, read that UEF file, the record, now I'm going to get the next record and get Mr. Hansen. Basic. It's not so basic at all. It's really a sophisticated language on OpenVMS, isn't it? It has the very best RMS integration. It actually knows about RFAs. You can say, just like seek and tell, you can do a get RFA and a find my RFA and get by RFA. It can connect multiple streams. It does segmented keys just fine. It can do user opens. It's a good language for RMS. It's also gets a little bit more verbose because it wants to make sure you open the right file. So I'm going to describe my record first. I'm not going to do it on the fly like DCL, but I'm going to describe the record first. A UEF record looks like, well, a simplified version of a UEF record looks like 4-byte fill, some username, 12 is enough, a fill to skip over all sorts of last login date and password and stuff because I don't want to see that now. Then I have a byte with owner length and I have a string with the owner text being adding up to 31. So now I open up the file for input as file number, index, record type, any map, the record layout being that UEF layout, get using key 0, I could have used key 1, key 3, with this key value, make it equal, which really means it needs to start with Hein, so it's kind of greater or equal. If I needed an exact match, I would have had to put the 8 spaces behind there, right? I print the result, username, and the segment from the owner, from the start of the owner to its proper length in case there is funky bytes there. And now I do a get for the next record because I didn't say anything else, and I'll get Hein and Hansen, just like DCL. COBOL. Oh. We're getting verbose, but not as bad as C. We have to describe the file in detail, saying where the username is, or what the key is. We have to say, so in BASIC, we didn't have to tell it where the key was. Just know I want key number 0. COBOL, the key value sits in the record. I lay out my record in this crude way again with username and owner length and so on. And then I can finally, that's the setup for COBOL. And it looks similar, really. Begin here, open for IO or read, whatever you like. UEF file allowing all. Move behind the username, read the file where key is that username value. That could have been a different storage cell. An invalid key, just stop. Display username and the owner, and then read UEF record next versus key is, and at the end stop if we run into the end, and that gives the same result. I didn't put the result there, but it gives the same result. Trust me. C, now we're going to talk FABs and RABs. So C, bunch of include files, we allocate a FAB, we allocate a RAB, we declare our record in Hein's way. It's just a quick and dirty hack, of course. We start our program. Oh, I got that twice. Never mind. I initialize my FAB to say this really is a FAB. There's a length and a code in there to say I'm a FAB, and make the rest zeros because it could be random stuff, right? I move the individual information in place. The file name address pointer is going to point to the file name, and the file name size is going to be the length of the file. of what is pointed to. And I go on, I set up the RAB to point back to the FAB. I tell it to go in key mode. Key buffer is filled with Hein, the key buffer is the string Hein. And finally, I'm setting up a pointer to a buffer. I open my file. Yes, I'm doing the get. And I switch back to sequential mode to do more gets until I'm done. And I made that, I think I made that item 2 to begin with, so I'm going to get 2 records in this case. And I print the record through the formatted string, and we're happy. And maybe this was my proudest moment on Sunday when I finally finished the presentation. I wrote a Python program. I found one and I cut it to pieces and made it do what I needed to do. Python is a pretty nice interface to RMS. Looks simple, but it does all I need to do. It's a nice object-oriented support package, simple, powerful. There's really a bunch of good examples, so find them and once you install Python. And there's some documentation in the wiki, and it was enough for me to get going on it and look what it does in the end. It speaks RMS to a degree, so I import some header files, and I declare a variable UEF path, my file name. You've seen it before, and then I'm going to speak RMS. I'm going to say the file options, no file options, my file access is to get, my sharing is all of these, I share with all of these. I create a handle, my UEF file is the RMS file for this path and those options. If I don't speak the right words, tell me. And then, it gives back to this is fun. On the handle, you can find a method to get the full name and the number of keys. Handy thing to have. Nothing to do with getting the records yet. And now we get to work. The key is Hein. Let's read a record. Oh, I'm telling it to use key 0, not key 1 or key 3, but to use key 0. I execute the fetch method using the key. It returns the status and a record. And I declare the fields for that record. Now, this is a kind of copy. You don't want to figure this one out on your own, but it says there's an integer and there's a 32-byte string, and there's a half integer and a full integer. I think that's what it means. And another 32-byte string. You get the drift. I read my record. I unpack the record into fields. And I print the result as field 1 and field 7, in this case, from that formatting string, and say, do it. Poof, there it goes. Plus it says it's reading this file with 4 keys. That's the bonus method that were available on the file handle. And I'm gonna leave it at that. And the fumbles have to read. Do I read a fumble? This is just my little gripes on RMS, if you like. After 30 years, 40 years, 50 years, it's a good system for non-database, free with the operating system, right? It satisfied needs for all your COBOL basic Fortran programs. Few things could be better now with the technology today, but 50 years ago it was a cool design. I think VSI, we could have done a little bit more. But there was no customer that says, here's 2 weeks of work, implement this feature for me. People whined, of course they do. Is there money on the table? Not really. So mostly the thing is that we still stuck with that 16-bit record size. It seems so limiting. The 32-bit VBNs, the relative record number, although I don't think anybody has complained about needing more than 44 billion cells. 16-bit record ID, so those records in index files have a number. You can actually run out of that number and create a mess. It keeps on working. It doesn't complain, but it's not happy. The 63-block bucket size, I really find that very strange. We could just make it a byte instead of the 16 bits. I don't see why we couldn't, except for 4 weeks of work or something like this. Yeah. And we already have a precedent because we do in sequential files, we can 127 blocks and 255 even, I believe. It's all internal work if we did that, because you didn't need to know how big the bucket was for the thing to work. But if you want to get some speed, you do need to know. Tiny thing. The first bucket just starts after that prologue. And it would be nice if all the buckets were nicely organized on storage boundaries. But we cannot achieve that by default. I can do it, but it's not there by default. Duplicate keychains. We promise in 1987-88 that if you put a record, if you have one Hein and a second Hein and a third Hein, we will give them in the order they were added to the file. Promise. Forevermore. Now, if you have 60,000 of them, you have to find where to put it, and we can only store like 1,000 in a bucket. So you have a bucket, say, no room here. Next bucket of Heinz, next bucket. So you do 63 IOs or 60 IOs to find a room to put the next pointer. I don't know. I've not really thought through it much, but maybe, just maybe, there could have been a last known end. So if I'm starting down the chain and it's more than 2, maybe I should just scribble down. When I find the end, I should scribble it down somewhere and remember to pick it up next time. But we didn't. Convert reclaim is standalone. If you want to clean up that file internally, restructure it, it's standalone. It could just be a privileged program and take out a bunch of lock and do it when it sees an opportunity. Could have done that. And then those RFAs are wonderful and powerful, but we keep maintaining them all along, and maybe nobody ever uses them, ever. So there should be an option to say, don't bother with the RFAs, just keep your records in order, and nobody will ever go back to remember where it used to be. That's that for the advanced users there, those gripes, I don't know whether you sympathize or whiner. That's my story. I hope it was not too, it was detailed, but manageable.